Great. Can you guys see my screen?
It's loading.
There it is.
Yeah, I see it.
Cool. Yeah, nice to meet you folks. My name is James. I'm part of Orbit Fab. I'm one of the principal engineers here, and we're kind of the gimmicky tagline for our company is gas stations in space. So this is kind of just a brief overview deck, and we can kind of center the discussion around maybe a Q&A after. Jump right in, quick company overview. The mission of Orbit Fab is to build an in-space propellant supply chain. And we do that by, we see kind of a future in-space economy that leverages ubiquitous supply of available and readily available propellants of different types. And kind of the overall vision to support this is a bustling in-space economy. And we're pretty gung-ho about kind of, supporting permanent jobs in space. Fairly high-level highlights of the company. We were founded in 2018, so we're fairly new in the space, so just a tad over 5 years. We're headquartered in Colorado, and we recently moved to this Colorado facility and transferred our headquarters from San Francisco. And then we just opened the UK office this last year. We're about 63 as of today. When I joined the company, it was 2021, a little over 2 years ago, and I was the 8th employee. We received investments from Lockheed and Northrop. We're the first company to ever kind of have a co-investment from both of them. If you're aware of the traditional kind of defense prime space, Lockheed and Northrop are kind of, they're big competitors of one another, so they don't, tend to play nice a lot of times for investments. 2 successful space flight missions. So right after we founded the company, we launched an initial payload to the ISS. That's what's depicted in the top right. And then 2021 in the summer, we launched Tenzing, which is the bottom right, and that's kind of a 16U plus CubeSat that we launched into SSO, and that's the first tanker that we've launched. So that's an HTP satellite. Let's see, we're the first private commercial company to resupply the ISS with water. So our fill drain valve, our docking interface and fill drain valve replacement is called the RAFTY. That's baselined on multiple DoD and commercial satellites as of today. And we're the first commercial in-space fuel sale. We facilitated the first commercial in-space fuel sale deal with Astroscale early last year. And we're working towards refueling a DoD vehicle in geostationary in the 2025 timeframe. Snapshot of our architecture, we have a kind of a two-pronged approach. So we have passive, we look at it as passive versus active. You can think about it as kind of, simple vehicles versus more complex, more capable vehicles. So the fuel depots are the fairly passive and simple vehicles. So they're purely an aggregate and a common location of multiple individual propellant tanks in various kind of highly trafficked orbits. And then the shuttle vehicles, the fuel shuttles depicted coming between Cislunar and Geo. Those are the highly capable kind of 6 degrees of freedom control satellites that shuttle fuel from the depots to the end client. And you can see kind of Astroscale's Lexi depicted in Leo there. So our commercial business model is really predicated on 2 kind of cornerstones. So on the left-hand side, we have that RAFTY service valve. So it's really just a piece of hardware. It's a very standard it serves a standard purpose. So every vehicle that's launched into space that has its own propulsion system needs to have what's typically referred to as a fill drain valve, and that's to access your propellant tanks and fuel those propellant tanks on the ground before being processed and integrated into the launch vehicle. So Rafty kind of serves that purpose as a vehicle designer so that you can kind of hot swap this in. We made it fairly competitive on price and what a typical satellite designer will care about, which is kind of enveloped in a term called swap C. So it's size, weight, and power. So we certify Rafties for use on kind of partner propulsion systems, and we're working through partnership programs for those propellant or those propulsion system manufacturers, as well as spacecraft bus manufacturers. And then this is all kind of just a foot in the door to our true business model, which is selling and delivering propellant in space. So Rafty not only does the fluid transfer, but it also facilitates the mechanical docking. So our client is basically in space with a Rafty service valve, and our shuttle vehicles come over with a basically a male version of this coupling that's actively powered and mechanically docks with that vehicle prior to facilitating that propellant transfer and resupply. But we want to develop and operate in space infrastructure, and really ultimately, once our business model is kind of maximized, we'll really become a logistics operator in space. There's a few reasons why someone might want to refuel. So depending on your application as a spacecraft designer, spacecraft operator, we can extend lifetime. That's kind of the traditional value add for refueling. But it also gives you a lot more flexibility. A way to think about it in kind of the business frame of reference is you can trade CapEx and fixed costs up front to more of an operational expenditure over time while you're already in orbit. So, you have a large vehicle, large percent of that mass is propellant, and your launch costs being directly related to how much mass you're trying to send up there, you could send your vehicle up partially filled and immediately start generating revenue with that asset in orbit. And once that half tank or partial tank is depleted, you can coordinate with us and we'll come and resupply and extend that life. But now you've added a lot of flexibility as far as what you can do with the amount of money that you're operating with to start with as a business. A lot of our DoD customers are really focused on that middle bucket, but mobility is kind of it's the crux of being able to operate your network of satellites in a way that's dynamic, and a way that you can. It adds a lot of value as far as resilience in that network of satellites and those vehicles. It can give you a lot of flexibility beyond what those vehicles were initially designed for, like the fixed Delta V budgets. Those satellites might have initially been designed on paper to perform, and it adds a lot of kind of value in the DoD space. We also provide a lot of logistics modeling support for kind of planning out the strategic, cost, like dollar value add for your particular, satellite service through our in-house software platform we call Umpire. Yeah, so this is kind of a simplified chart going through some of the value adds that we just spoke to. So it's really flexibility. That's a lot of the power that you get from having propellant supply available in space. So this next section goes into a little bit more about the Rafty product itself. So our interfaces reflect kind of how we approach our in-space architecture, our vehicle architecture. So Rafty on the left-hand side is more of a passive valve. So it's not an electromechanical device. It's not powered. It's passively actuated. And it stands for Rapidly Attachable Fluid Transfer Interface. So we have dual cores. You could plumb them into your propulsion system. You can have, fuel aux. You can have fuel and pressurants. There's a few different options. You can plumb them both depending on, the performance that you're looking for. And it's also that passive docking fixture as well that mates and interfaces, with the grip. And so the grappling and resupply interface for products, that active component is on all of our shuttles. And so that is an electromechanical device that basically the acronym that's used to describe those space operations called RPOD, RPOD. So it's those shuttles perform rendezvous, far field rendezvous to near field, proximity operations once we're kind of in that sub-kilo relative distance from your target, your client, and then the actual docking, the docking between and the mechanical mate between those two vehicles. And so the docking portion is entirely facilitated through this grip mechanism. Yeah, so we just sent this out to the Air Force Research Lab down in New Mexico and did a bunch of testing on the ground hardware, which has been pretty fun. So these Rafties are commercially available. We didn't really, it wasn't a fundamental part of our business model until we looked around the industry when the company was founded 5 years ago and found that there was no commercially available docking or fluid transfer interface. So we've kind of set down this path to develop it in-house and qualify it to kind of the standard flight industry standards. Let's see. So Rafty, we're kind of constantly iterating through. So we've launched a bunch of Rafties out into space. We're constantly learning from operating them over time, and we want these to be, very cheap, accessible, fill drain replacement valve for your satellite. It's relatively light, 0.5 kilo. I mean, compared to normal fill drains, it's fairly competitive. And the volume interface is competitive as well. It has to be externally mounted, obviously, for that shuttle vehicle to come in and dock with it. We're qualifying our initial batch for those DoD missions, and they're currently for monopropellant hydrazine. That's the propellant. The previous batch of Rafties, two of which we integrated and fueled through on that Tenzing vehicle, that previous flight vehicle, was high test peroxide. And that's a pretty interesting propellant for kind of different reasons. If you're familiar with HTP or H2O2, it's one of the few propellants that are able to be processed and derived from lunar ice, or any ice for that matter. A lot of the ISRU discussion today is really founded on the LOX and hydrogen propellants. So your standard, it's basically your highest performance, but it's fairly difficult to manage the hydrogen, and they're cryogenic propellants. but we see HTP kind of as our horse in the race long term, where your 30 seconds of ISP difference doesn't matter that much once there is large scale processing of those materials off world. Yeah, the ISIU is a super interesting kind of topic that we like to think about to be strategic about our decisions today, because we see a lot of the supply chain impacts of ISIU down the road are going to really augment which propellants win out for in-space prop. We have 3 inhibits to overboard leakage. This is all kind of engineering lingo, but basically it's safe. It's rated for toxic or hazardous Class A propellants as the range safety industry standard. It's called ASPECMAN. Kind of dictates how you design for safety critical applications. We use compatible seals, and we have passively actuated covers to mitigate direct line of sight exposure, and it's really just to mitigate long-term like atomic oxygen. It helps a little bit with radiation. But yeah, the RAFI we designed to kind of capture the bulk of the market for vehicles that we see right now. So we've rated it up to handle loads to 10-ton spacecraft. Nothing super exciting here, but basically we have a RAFI users guide on our website that is for previously established partners or potential partners that we're working through refueling their vehicles and baking in RAFI into their designs. And it basically just gives you high-level requirements that your vehicle needs to meet for us to be able to come and rendezvous and dock with that vehicle and transfer propellant. A few missions that we're working through right now. Yeah, so this is the one I mentioned earlier, but FURPHY, it was a flex tank and an active pumping demo that we launched to the ISS. And I guess the more interesting thing here is really the turnaround. So like ATP or authority to proceed, once we signed the contracts with the ISS National Lab, we only had 4.5 months to launch. And for anyone in there who's designed even like fairly big, like 3U CubeSats or something, 4.5 months is pretty sporty. So there's a lot of kind of rapid development going on. And this was all out of our tiny little garage that we had in SF. But yeah, we're the first private company to supply water to the ISS. Tanker, this is the mission that I kind of joined at the head of. So fairly small vehicle, 35 kilo, that's wet math. This was a 9-month kind of mission or program timeline. So that this was also very sporty, but it's filled with HTP. We went through a lot of shenanigans down at the Cape when we were doing payload processing and filling on the ground, but we got it launched. It's still operating today. And so it's really we view it as an on-orbit lab or like a test bed. So we're experimenting a lot of our far field rendezvous, RTOD algorithms, and it has a few vision systems. It has it has 2 propulsion systems actually, and a big kind of valuable data set that we're gathering from this is long-term compatibility and storage for HTP, which can be fairly difficult to manage over time. Pod Racer is one of the 2 primary flight missions we're focused on today. So we're trying to launch and integrate onto a transporter launch in 2024. It's a kind of your standard ESPA class vehicle. So it's, I want to say 215 kilograms fully loaded. We're using a bus partner, and this will be kind of the remaining buckets of risk buy down that we need before we kind of engage in in our commercial refueling service. So it's a lot more of the RPOD algorithms testing. Let's see. So government contracts, we're working on 2 government programs. We call it Rancor and Camino internally, but basically we're on contract to deliver up to 100 kilograms of hydrazine to a DoD asset in geostationary orbit. And then that timeline is 2025. So we're kind of cranking through these 2 flight missions right now. Key commercial deals. So we have that fuel cell contract with Astroscale, and we're working through another one with ClearSpace. So we're a partner on their kind of UK SA program to, I believe it's remove a fairing segment in LEO orbits. But it's a pretty interesting program. And I think the interesting takeaway here is, for the business folks, like this is, there's never been a sale or, sale agreement for the transaction of goods in space, like in space for space. So this, getting this contract signed, it took basically, 2.5, 3 years of negotiations and hammering out details because there's no precedent to rely upon. The contracting mechanism was built up from scratch. There's, a lot of innovation outside of just the technology in space. Like it's a really interesting time to think about commercial space because of, all this, usually it's like miniaturized or different applications of pre-existing technologies that are integrated together for a novel application. But a lot of the innovation that doesn't get appreciated is the business innovation of how to build a sustainable, business model for a space company. Let's see, and that's the end. So I have a bunch of appendix slides, but they're all kind of more engineering focused. Yeah, I don't know how you guys typically structure this, but I think, more discussion and Q&A might be more interesting way to.
Yeah, we're gonna move on
go.
to the Q&A section.
Sweet.
Those of you on Zoom, you can just type your questions in the chat or raise your hand and unmute. I believe we already have a question in chat. I'll pull it up right now.
Sweet.
Few questions for Yan. How does Orbit Fab get their fuel up there, weight-wise, because fuel is usually heavy? And how do you refill your own devices once they are in orbit? Or you just run until they have no more fuel?
Yeah, thanks for the question, Sadie. It's a good question. So the first part, how do we get fuel up there? So we kind of view our depots as, the analogy is like second-class mail. So basically, most conventional launch vehicles today, they have a bunch of mass margin baked in. So, your standard launch vehicle is going to have a little under 10% of that mass capacity open right when they launch. And a lot of that is kind of, some of that is baked into whoever the primary payload is. They don't want others kind of adding risk to their program. But a lot of launch vehicle providers that we've been speaking with are very open to basically cutting super low cost per kilo rate deals for payloads that are kind of readily available. So our whole approach here is the depots, the fuel tanks that we're trying to send up there and aggregate together for access later through our shuttles. We design them in a way that's very low risk, very simplified structure, mass optimized for propellant, and go to launch vehicle partners and say, hey, let's drop this in if another payload doesn't make the cut, misses their deliverables to get that ticket to launch, or it's a heritage vehicle with a bunch of flight data that will start to go into that excess margin that they carry. I hope that made sense. Let me know if it didn't. So how do we refill our own devices once they're in orbit? So a lot of this is, that comment I made earlier about like really we're going to become more of a logistics player in space. Basically, most of the propellant we're going to stack into those key orbits, and as they get used up, it's going to be deorbited basically, or passivated into a graveyard orbit, which is typically what you do for geostationary vehicles. But obviously, long term, we see more supply coming in from off-world sources. I mean, this is like 10 years plus down the road, but that whole ISRU mentality. Cool. Yeah, I hope that wasn't too rambly. Sweet.
Aiden said he has some questions. Aiden, if you want to unmute.
Oh, yeah. Are you done with your presentation?
Yes, sir. Hop on in.
Okay, I actually have like 10 questions.
Sweet. Let them rip.
I mean, it's a lot of them are just like yes or no. Are you gonna do ion engine refueling?
Yeah. So I didn't really touch on that. So our primary focus right now is low pressure propellants like chemprops. So we have that HTP. It's liquid based. It's the monopropellant hydrazine is, it's like the OG of OG propellants that they've been using it since like the 50s. All liquid based, low pressure. High pressure EP system, ion thruster propellants is 100% on our roadmap. We're about 6 months later on that. So our high pressure valve that's compatible with RAFD, is 6 months out, and then the compressor and the transfer mechanism is kind of that similar 6 to 12 months out.
Okay.
But yeah, we care a lot about the EP space as well.
Okay. Next one is, are you gonna have stations orbit, like the gas stations orbit between planets to allow like satellites like the Juno probe that went far out in the system to refuel and keep going around the solar system and doing all that stuff?
Yeah, totally. So, I mean, long term, we're very interested in unlocking planetary exploration and science. The real kind of short of it is we're a commercially, we're a venture-backed company. We're commercially focused. We need to generate revenue today, and all of our customers are in LEO and GEO. So, long term, there's some government demand for cislunar, and then there's some civil space for, further out into the planets. But right now, our core focus is Earth orbits.
Okay. And on the planets, are you gonna like planets and moons? Are you gonna make stations on the surfaces? Like
on the surfaces. So
the planets and moons.
So station wise, I mean, like the long-term storage, like in those depots and shuttles, they'll always be in orbit. But we do have internal like R&D projects that are kind of, a few people focused on ISRU and processing technologies. So we just went for a tipping points for a recent NASA proposal for HTP processing on the moon. So like there will be infrastructure and processing, machinery on planetary bodies, on moon bodies. If we do what we want to do longer term, but it's not a focus right now.
Okay. How are you going to have the stations communicate with each other and with customers to refuel their spacecraft on demand?
So the question is, what's the comms? Like, how do we communicate?
Yeah. Is there going to be like a network of communicating, or are you going to have like a hub? So you have like, for like the Earth, you have, stations on Earth that communicate with all of the satellites or the stations that's near Earth. And then like for Mars, you could have a station on Mars and it communicates with stations near Mars more?
Yeah, totally. So that's a great question. So there's a lot of nuance to comms and how you go about it, and we've kind of run the trade across most of them. So for our near-term missions, we're leveraging ground loop communication. So we have both the client and our shuttle vehicles, our mission ops centers. We're going to be tied. We have pass-throughs between them. We're working hand in hand with our customers to have active data and telemetry from both vehicles every step of the way. And that's facilitated through ground loops. So that's both vehicles in orbit, on holds or different phases of our operations in orbit. We're going to be downlinking actively. And the actual RPOD is going to be a continuous telemetry stream as we go in. And then there's a lot of automation we bake in for backouts. I mean, we're approaching this very conservatively because, a collision in orbit is absolutely a non-starter for us. Your question went into Mars and kind of more out there. Again, that's not our commercial focus today, but basically we need near real-time communications, and that necessitates basically a relay network of data relay satellites, which is a real commercial need today. So there's companies working on lunar data relay satellite networks today, and I'm sure that'll be a demand or a necessity as we grow out further into the solar system.
Cool. For the you're probably going to have a whole bunch of these throughout the system. So how would repairs for the stations work?
Sorry, say that again. How would what work?
Repairing, like
Oh,
maintenance, making sure that the equipment works, and you maintenance it once every like 5 years, or because for like spacecraft every so often they have to get completely checked out and make sure they have all the working parts and all that stuff.
Yeah, repairs are a pretty interesting thing. So this is kind of a subsegment of the servicing, in-space services industry. Basically, there's a lot of different players, like a bunch of different startups that are working on one. It's like fault detection and monitoring. So they'll go up and provide a service where they can go up and check out your asset in space and basically verify or give you a warning that repairs or maintenance are required. The actual activity of repairing and maintenance, like that's order of magnitude more complex. And so I guess the way we're thinking about it right now is we're designing very robust, long life, 15-year geo-life shuttles. And then on the completely other end of the spectrum, those depots are glorified propellant tanks that, at the end of life, we're going to passivate. So repairing isn't really baked in, basically, near term. And it's not really, it's definitely not a commercially available, off-the-shelf service right now.
Yeah.
But it's super interesting.
Yeah. Okay. And then at the beginning, I was kind of talking about it, but the actual fuel itself, I know you talked about the kind, but are you going to go mining the asteroids to create the fuel in space, or go mine the fuel on the moon or something to refill those stations?
Yeah, so we don't really talk about it, but long term, we're open to supply of goods regardless of where they're coming from. So like today, our entire business model is predicated on fuel supply, propellant supply from the ground, from Earth. Asteroids and moon and all that stuff is super cool and it's fun to think about. It's just not
it's not viable,
it's not commercially viable today.
Okay. would that probably be a thing that you would outsource? And your company just focuses on the refueling aspect?
Yeah, basically. So we see ourselves as, longer term, once we're looking to dominate the refueling market and then go out further into more of like what you would see as a standard, like what your petrochemical processing company on Earth is today, and go more towards like, what do you call that, up the supply chain, but basically more into refinement and processing. But again, we're very much deadlock focused on just providing propellant to commercial customers, that refueling end-to-end service today.
Okay, I got two more. Sorry, I was doing it as you were doing your speech. Who are your competitors right now for the refueling stations?
Yeah, great question. So there's no direct competitors. Our closest competitor is actually, one of our investors, Northrop Grumman, kind of a frenemy situation, but they have a product in space called the MEV, Mission Extension Vehicle. They've launched 2, and one's hooked up to one of the Intelsat satellites that got a little bit wonky. They had a propulsion system fault. And so they're basically, I say it's like adjacent and not direct competitor, because the service itself is kind of fundamentally different from us. So their MEV vehicle latches on and provides all that propulsion. So it's a form of, life extension, but that asset is now tied up directly with the Intelsat vehicle. So it's a one use, at the end of mission, that MEV is going to be deorbited. Whereas kind of our approach is more facilitating the transfer and resupply to multiple vehicles. So the revisit rate on a single shuttle will be, ideally more than 10 is kind of what we're shooting for, if that makes sense.
Yeah. Have you seen the SpaceX video where they have 2 starships and one's refueling the other?
Yeah, the tanker. Yeah, so
what would that be?
Starship tanker is super interesting.
Sorry, keep going.
Well, the tanker concept is super interesting. It's the only way to get the mass into lunar orbit that they need for the Starship concept. Kind of a fundamental difference is the volume of transfer is like somewhere in like 2.5 orders of magnitude more than kind of what we're trying to do. And they're both, it's a methalox engine, so it's both cryos, very different. We're purposely not trying to resupply cryogenics. One of the rationales behind that is, again, that ISP, that efficiency difference really gets eaten up once you have multiple resupplies available for your satellite. So the mass complexity of having a cryo, like in-space propulsion system, is basically a non-starter unless you're like a really well-funded, more or less like a governmental mission. Commercially, I mean, there's a reason that there's no cryo in-space propulsion systems.
Gotcha. Okay, my final question. I thank you very much for answering all of them. I don't know if you said this towards the end because I left for a minute, but do you have investors coming from other countries, or are you working with rockets from other countries or agencies like the ESA or JAXA?
Yeah, so we have 2, to be transparent. So right now today we have no non-US investors. We have 2 that we're talking with, and we're going through. There's a lot of regulatory processes that we need to follow to explore those investments more. So like, so no is the short answer. But yes, we're open to it. The nature of our business means that our core technology is all ITAR controlled. So, you know, even with our UK office, we follow very strict protocols on what type of technical information we can share with that office. So, you know, it's basically a lot more difficult if we were to go down that path.
Gotcha. All right, well, that's all the questions I had. I really appreciate you help me answering all of them.
Yeah, absolutely.
Okay, want to open it up to the floor? You guys got questions?
Sure. I had a question more like the design side. What was your guys' design philosophy for Rafty? Like it reminds me of like an electric outlet plug or you know, electric cars is what comes to mind for me. What were the kind of the requirements you guys set for yourselves of like priorities of like speed or durability or what kind of things went into that?
Yeah, great question. Design requirements and our kind of philosophy on design. So a lot of this, which I personally found novel from my previous companies, is we did a lot of market surveys. So we went with our, you know, partners, our customers, our potential customers at that point, and then basically just interested industry players, and had a bunch of survey data that we collected on, hey, if we're building this like, you know, commercial refueling interface, what would you want it to do function and performance wise? And then those kind of set the foundation for how we designed the thing to do. Design approach in general, it's very iterative. So, you know, we know that we call the current one block 2. We know block 2 is not going to be perfect. The whole thing is reducing the cycle time from hardware development, hardware manufacturing, and getting that hardware in your customer's hands, so you can get real life usage and testing and feedback.
That's really interesting. I didn't think about the fact that like kind of the boring part of on the earth would kind of take precedence of like manufacturing it, but it makes sense. I kind of a follow-up question to that for the grip interface. Is the idea to keep that proprietary, or again, like the metaphor of the like electric car plugs, or maybe even like normal gas station? I think it's all kind of standardized. Would that be a viable business plan to make it more open source so that more people can use you, or is it the idea to get more per customer by having a proprietary design?
That's a really great and thoughtful question. So the way we've been approaching it to date is the Rafty, we had basically, you know, we're open to giving it away for free, and there's a lot of strategic reasons for this. But we have something called an open license. So basically all that IP, if you want to develop and build your own Rafties, you can, and we're actually actively exploring manufacturing partners that want to get into that business. The active side, we see a lot of defensibility, and some of this approach is like, you know, we see our moat being that active component, both in grip itself, but also the shuttle network. A lot of that is basically it's like, you know, it's probably an order of magnitude or a little bit more complexity and you know, in-house expertise that you need to develop to control both of those, like grip and those shuttles. And so we're kind of keeping that closer to the chest. And long term, you know, we want this to be adopted as the standard, the interface. And if you see, at least across most organizations in the DoD, the way they write their proposals, we're actually, it's something called GFE, Government Furnished Equipment, but basically a lot of those Rafties are baked in to a lot of these programs. And that's kind of indicative of our approach of making it a standard. But again, that active half we're keeping a little bit more proprietary.
Thanks.
So we got 5 minutes left. Any more questions via Zoom or in person?
I got a quick question. So my name is Ryan. I'm a finance major. This is actually my first time coming to the space business association, but you know, it's just interesting to me because this is all kind of new to me, I guess. So you were saying that the business model part of it's important, and so I guess would you guys be looking to hire like people with finance background for your company? And then I guess just a second question to that, where do you see the industry going in the next like 20 years, just long term?
Yeah. Nice to meet you, Ryan. So the first question, I would definitely think so. I mean, I don't know if we have active like a finance role that we're looking for, but in general for the industry, I think there's a huge kind of gap. Like traditionally, you go to like 20 years ago, the industry was so static. Like it's all like people from like those defense primes, those tier one contractors, building the same rockets that they developed in the 60s, 70s. Mainly just like engineering dudes. And in the last 10 years, it's kind of been opening up a little bit more with this commercial space movement. And I think there's a continued need and demand and a lot of value from people that aren't just traditionally like aerospace engineers. So yes, to the first one for sure. The second question, 20 years, I mean, I ideally see a future where there's robust economic activity and business activity, both in space for Earth and in space for space. And those can be the transfer of goods and services. So one of the things I'm pretty bullish on are a lot of like advanced materials development and R&D that's available in orbit. That leverages the ubiquitous vacuum and kind of the zero G properties of heat transfer basically to make some really gnarly materials. So the company I was at previously, Main Space, we developed the Z-bland manufacturing process. The Z-bland, if you're familiar, is like fiber optic cable that all the data transmission today, at least the high bandwidth stuff, is all through fiber cables that are routed. There's like a big one across the Atlantic floor, right? We made Z-bland samples that were 1.5 orders of magnitude, it might be 2 orders of magnitude more efficient in data transmission, and that's like just one tiny random material application. But basically robust goods and services for space, for Earth and for space versus space. That'd be pretty sweet.
I'm curious, what is it about zero gravity that allows you to build such efficient materials?
So for Z-bland specifically, the zero G app was we controlled cooling at a rate that's just not possible on Earth. So like the effect of gravity, when you think about atoms colliding with one another, and because this is like it's basically an optical crystal, right, that you pull. And so on Earth, when you pull it, like it's a fairly crude way of heating and cooling, and the whole time the gravity effects basically make those atoms collide internally at a rate that's much higher than what you can do in space. But there's so many different ways to leverage that for different materials that I'm not aware of. But a big thing is like pharmaceuticals and pharmaceutical research and stuff. There's a lot of pretty interesting like biotech stuff of like cell fabrication and manufacturing. I'm not too close to it. I'm not aware of the kind of deep technology behind it, but they do a lot of that research on the ISS right now.
I got one last question. Have you done any research into or any partnerships in general into these commercial space stations that Blue Origin and other companies are developing? Because I'm sure they will need to refill as well.
Yeah, definitely. That's definitely an angle that we're pursuing actively. For sure.
All right. Anyone else on Zoom?
Yeah, I have one question, and I know we're getting short on time. I can't believe that the whole hour has gone by. So I'd just like to thank you again, Mr. Cho, for coming out here and sharing all this with us. I don't think one person. I think we all have multiple questions that we could ask. I mean, Aiden absolutely led the way with writing and giving 10 questions. And I'd like to leave with also a multi-part question. Since you're such a multifaceted guy. I mean, you've presented all this very professionally, but also very technically. So that shows that your background, you've been able to juggle the business lingo of things as well as the very technical STEM lingo of things. And I think that's what it takes to succeed in any industry, especially the space industry. So my question to you is, what's the most difficult challenge, whether engineering or business, that Orbit Fab is facing? How are you guys addressing it? And then is there a lesson that you can take from, from a challenge that you in your personal resume, career, life, that you've overcome? So how have you overcome a challenge? How is Orbital Fab overcoming a challenge? And then how can we follow the example of this company, which is completely changing it's building space infrastructure, which is just amazing. It's like the future is here. So yeah, those are my questions. And thank you again.
Sweet. Yeah, no problem. Thank you, Tim. So keep me on track if I ramble a little bit or lose track of the parts. So the first part was the most complex or whatever. A really interestingly complex problem that I just came across this last week, which it's really interesting because it's more out of my depth. So I'm more of a standard like propulsion engineer guy. So contracting mechanisms to mitigate our risk in the context of purchasing bulk propellant that we pre-sell to a customer. So like, I'll give you in very specific terms. So we have a customer that wants 1,000 kilograms of XYZ propellant that's accessible in orbit, basically 4 or 5 years from now, right? And this asset, this propellant itself, is not traded. The supply volume is not such that the pricing is commoditized, right? You can't go in exchange and see that commodity pricing, and it's very volatile. And it's even in the last year, it's been impacted. It's gone up 2 orders of magnitude and down 1 order of magnitude in the context of global conflict, hindering supply. So the problem is, how do we buy options to buy later that asset at a price today that on one side doesn't expose us if that price just plummets in the future and we're just completely exposed, or does it in a way where the only handful of global suppliers of that propellant or that asset, one, don't eat our lunch, or they get overly exposed to the risk. So it's like basically everyone's trying to like hedge, but also like we need commitments for that propellant sooner rather than later. And then
so it seems like collaboration is going to have to come into play. It can't be strictly like if everyone is trying to cut everyone's throat, fuel might not end up getting to space at all. Something worst case. And then to clarify my later question, what would be some advice to us? You've been able to build an amazing career. What would be an advice for this group of students right here and everyone that's going to watch the recording in the future, college students, people that have ambitions in the space industry, whether engineering or business people, like my friend mentioned with finance.
Totally. I think the biggest one is don't sell yourself short. You have value. You're an asset. You bring a different approach, a perspective, and way to think about a conventional problem that maybe needs and gets value from that different perspective. I think engineers are really guilty of this a lot of times, where sometimes we're kind of like hardos about like it's only technical problems, like that's the only challenges, but there's so much nuance, especially to a nascent industry like space. No one's really making a lot of money in space right now. If you look at the investment dollars, like in the last 10 years, it's so interesting because most of that money is funneled into launch vehicles. If you look at total like GDP, like total productivity and value created, like those launch vehicles are very small. There's a lot of value add in different areas. Never be afraid to like reach out directly to someone that is doing something interesting in space, to have a conversation, pick their brain. Just be interested, be engaged. I think that's really a big thing. I mean, it's so new, right? Like there's so much to learn, there's so much to do moving forward, that I can't imagine people just shutting doors in your face, on cold outreach and things like that.
Speaking of opening doors, next week we have our LinkedIn workshop. As James already said, it's great to reach out to people who are doing interesting things in the industry. You never know what connections you're going to get. You never know what doors you're going to open for yourself if you just cold call, cold email, or cold message through LinkedIn. So make sure you don't miss next week's workshop on LinkedIn development. And thank you again, James, for coming in.
It was our pleasure.
Thank you so much,
Thank
guys.
you. Yep.
Yeah. All right. Cheers.
All right, I'm going to stop sharing and stop the recording.